We are now in Chapter 7, Section 2 of your textbook, which is Theoretical and Experimental Probability. I'm hoping that this lesson will be pretty straightforward. I know it looks kind of scary and long, but it's actually fairly simple. The first thing we're going to take a look at is theoretical probability. Now, the first thing we need to talk about is what exactly do we consider to be probability? Probability is the measure of how likely it is of an event occurring. So each possible result of a probability experiment or a situation is called an outcome, and then the sample space is the set of all possible outcomes, or the total amount of outcomes possible. And an event is an outcome or a set of outcomes as well. So you can see right here we have an experiment or a situation, so something that's very frequently used in probability is talking about flipping a coin, landing on heads or tails, rolling a number cube. Usually we use a six-sided die, so that would be the numbers 1, 2, 3, 4, 5, and 6 on it, on each face. And then we also use spinners. So what's the probability of it landing on blue? What's the probability of it landing on yellow? Stuff like that. If we're going to be using theoretical probability, we're going to use this equation right here. So theoretical probability of an event is a ratio of the number of favorable outcomes over the number of outcomes in the sample space, which basically is just saying how many times does that event occur, and then how many outcomes did we have in total. And last bit of terminology is a complement. So usually when we think complementary, we think of something that goes together. Well, it's kind of the opposite in probability. The complement is the probability of an event not occurring. So to find the probability of an event not occurring, we would do 1 minus the probability of that event occurring, because each probability is a fraction, so it's usually going to be less than 1 or equal to 1, or it could be 0, but it's never going to be larger than 1, so we always should end up with something or the number 0. Okay. Let's take a look at example 1. Hopefully this will all make more sense when we start actually taking a look at the problems. So example 1 is where we have a spinner and we just want to find the probability of each of these events occurring. So number 1 says, what is the probability of landing on an even number? Well, I'm going to have to put the number of favorable outcomes over the number of outcomes in the sample space. So when I look here, how many even numbers do I have? Well, I have 1, 2, 3, 4 even numbers, because 2, 4, 6, and 8 are even. So that's 4 numbers out of the total amount. So how many numbers do I have on the spinner? I have 1, 2, 3, 4, 5, 6, 7, 8. So 8 goes in the denominator. Whenever you're writing probability, you want to make sure you simplify your ratios. So if this ratio is 4 over 8, I can simplify to 1 over 2. Number 2, what's the probability of spinning the spinner and landing on a number that is less than 3? So when it says less than, it means a number strictly less than, or not equal to, or greater than. Well, the only numbers on the spinner that are less than 3 are 1 and 2. So there are 2 favorable outcomes out of 8 numbers total, like we had discussed before. And I could simplify that, so I'm going to. That becomes a 1 to 4 ratio. Number 3, what is the probability of spinning and landing on a 5? Well, if you take a look at the spinner, there's only one number 5, so 1 out of 8, and that's already simplified. What's the probability of spinning and not landing on 7? So This right here is an example of the complement. Whenever it says what is the probability of something not occurring, we just do 1 minus the probability of it occurring. So if it's probability of not 7, it's 1 minus the probability of 7, which is 1 minus, there's only 1 7 out of 8 numbers on the spinner. And 1 minus 1/8 is 7/8. You didn't have to do the complement. You could have just used common sense. What's the probability of not landing on 7? Well, there are 1, 2, 3, 4, 5, 6, 7 numbers on the spinner out of 8 that are not the number 7. And hey, looky there, we put 7 over 8, which cannot simplify any further. All right, number 5, what is the probability of spinning and landing on a 5 or a 6? So it could land on either of these, meaning we have 2 favorable outcomes out of 8, and we simplify that to 1 over 4. Number 6, I know it looks kind of funky. It says, what is the probability of spinning and landing on a 9? Well, there is no number 9. So that would be a big fat 0 over 8, which means there's a 0 probability or 0% chance that we're even going to land on a 9. Okay? Next, we are using the word Buckeyes in order to fill in the probabilities below. So when we have the word Buckeyes, just imagine that each letter in the word is put onto a slip of paper and we're just pulling from a hat or something, okay? What's the probability of pulling out a vowel? So when we think vowels, that's A, E, I, O, and U. Well, if it's a vowel, sometimes Y, but in Buckeyes, we're not going to use the Y. In the word Buckeyes, I have 1, 2, 3. So I have 3 vowels out of a total of 1, 2, 3, 4, 5, 6, 7, 8 letters. That does not simplify any further, so I'm just going to go ahead and use 3 8s. What's the probability of pulling out a letter K? Well, there's only 1 letter K out of 8 letters, so that would be a 1 to 8 probability. Now, 3 and 4 ask for the odds, but I'm not going to do odds, so let's just cross that off and move on. Next, we have a probability when rolling a number cube. So whenever I just say a number cube, I want you to assume that it is a 6-sided standard cube. So it has the numbers 1, 2, 3, 4, 5, and 6 on each face of the cube. So number 1 asks, what's the probability of rolling a 3? Well, there's only 1 3 out of 6 sides, so that would be a 1/6 ratio. What's the probability of landing on an odd? 1, 2, 3 of the numbers are odd. Out of 6, that simplifies to a 1-to-2 ratio. Number 3, what's the probability of landing on a 7? Well, there's none. You could either write 0 over 6, which simplifies to 0, or you could just put 0. And number 4, what's the probability of landing on a 2 or a 3? So both of those are favorable outcomes. So 2 over 6 is a 1/3 ratio. So hopefully that was pretty straightforward and was kind of dragging at the end because it's so easy. Let's take a look at the second page. So now we're taking a look at what's called experimental probability. And all that means is that there is going to be an experiment conducted, and we're going to use that data in order to come up with a probability. You commonly hear this when you're at a doctor's office and they're like, hey, you need to have this done. It has an 80% probability of success. That means that they've created a database where they've kept track of their success in their surgeries before, and this is what it ended up with an 80% probability of success. Now, each repetition or each time that they try an experiment is called a trial, and the sample space is the total number of trials that they conducted. So when we're writing the experimental probability, we're going to use the number of times the event occurs, which is a favorable outcome, just like what we did on the other page, over the number of trials, which is the total, just like what we did on the other page. So for number 1, it says the bar graph shows the results of 100 losses of an oddly shaped number cube. Find each experimental probability. So when we're looking at the number of tosses of this cube, this bar graph's kind of hard to see, so I'm going to go ahead and write in what the numbers should be. So this is saying, hey, 17 times it landed on a 1, 21 times it landed on a 2, 16 times on 3, 11 times on 4, 22 times on 5, and 13 times on 6. So when it asks, what's the probability of rolling a 3? Well, out of this trial, it landed on a 3 16 times. So there's 16 favorable outcomes. And I need to put that over the total amount. So if you add all these up or just look in the directions, it says that there were 100 tosses. Remember, we should always simplify our ratio if at all possible. So this simplifies to 4 over 25. If you wanted to put a decimal, that would just be 4 divided by 25 or 0.16. So that means 16% of the time it landed on a 3. What about the probability of landing on a perfect square? Well, a perfect square is like, what's 1 squared, 2 squared, 3 squared, 4 squared? So 1 squared is 1, so that would be a perfect square. Or 2 is not a perfect square, 3 is not a perfect square. 2 squared would give me 4, so 4 is a perfect square. 3 squared would give me 9, and that's not on here, and all those other numbers would be larger. So what's the probability of landing on a 1 or a 4? Well, since both of these are favorable outcomes, we just add them together. So it landed on a 1 17 times. I'm going to add that to, it landed on a 4 11 times out of a total of 100. So 17 plus 11 would give me 28 over 100. You could plug that in a calculator or simplify it. That'd be 7 over 25, or that's 0.28. So 28% of the time it would land on a perfect square. Part C says, what's the probability of landing on something other than 5? This is like P not 5, which is the complement. So just to practice it, I would like you to put 1 minus P of 5 using the complement. So that would be 1 minus, it landed on 5 22 times. 1 can be written as 100 over 100. So 100 minus 22 gives me 78 out of 100, which is 39 over 50, or 0.78. That's not the only way you could have done this. You could have just added 1, 2, 3, 4, and 6, which is 78, and then simplified from there.